Hello students, my name is Shahab alias Varnami and I am Associate Professor of Chemistry in the Department of Industrial Chemistry, Aligarh Muslim University. So today we are going to extend our concept of chromatography, which we have already discussed in our previous slides about the introduction of chromatography, about the basic principle of chromatography, and we have also covered the classification of chromatography on the basis of the principle, on the basis of the format, and of course, the most important one on the basis of the mobile phase. So today we are going to explore the elution chromatography with regard to columns. Elution chromatography is maybe defined as it is the basic chromatography, or you can say simplest chromatography among all the various chromatographies which we have described in our previous slides. So today we are going to explore the basic concepts involving elution chromatography, the migration rates, the retention parameters, and also we are going to explore the selectivity of different chromatographic columns with regard to mobile phase and also the somewhat about the detectors. So elution chromatography, as the name suggests, so we will be these are our learning objectives which we have already said to you. So now quickly move towards the elution chromatography. As the name suggests, elution may be, in simple words, it may be defined as the washing away of analyte by the continuous application of the mobile phase. For example, if you consider a simple column, and here it is column, simple column is there. Now this column is actually, suppose it is packed with some stationary phase. Let me show you with this cross lines that this column is pegged, and now you have to separate your analyte, which is like this. You have to separate this analyte, and for say, let us suppose that it contains two constituents A and B. So initially what happens is that it shows you a very narrow band. This mixture actually exists as a very narrow band, and the moment you apply your mobile phase, what happens is this, that this band actually moves a little downward. This band moves downward little bit, and it broadens. This band broadens, and this broadening of band is actually called as the this broadening is called as analyte dilution. This is very interesting fact. This analyte dilution, and this column, this is the column. Now this band move for a little downward, and this is called as analyte dilution. Now you can compare that here this band is narrow, and the moment you start adding the mobile phase, you continuously add mobile phase, so this band broadens, and this band broadening actually tells you the story that now the migration or the distribution of the components has started, and this column is actually connected to the detector. This column is also connected to the detector, and as you keep on adding the mobile phase, I will show you here. You keep on adding the mobile phase, what happens is the band actually it starts separating into its individual components. For example, initially we have a two component system, that is A and B. Now after a certain period of time, after the continuous addition of the mobile phase, these two bands separated. For example, let us say this one is A and this one is B. And this, I've already told you that this is connected to the detector. Okay. Now, as you keep on adding the mobile phase, after a certain period of time, you will see that the component, that is the B component actually, that this B component is on the verge of elution. This is how the two components start separating. And these two components start separating because A has different affinity to bind with the stationary phase, while the component B has different affinity to bind with the stationary phase. And because of the difference in affinities, they are actually have a weaker and stronger interaction with the stationary phase. And stronger the interaction, the more time they are going to stay with the stationary phase. That is, they are going to elute at a later time. Now, if you draw a detector response like this, if you draw detector response obtained from the column and you put plot, for example, on the basis of time, then what you observe initially you observe is this peak, then you observe two peaks. Now, as you see that initially you add A and B, and finally the first component to elute was B. So in the chronogram, you will get first peak B and then you will get A. This pictorial representation of the migration of the two solutes or of the component with respect to detector response is called as, this figure is called as chromatogram. This is called as chronogram. That is, in simple words, it can be regarded as the migration fingerprint of different analytes of the substance which is to be separated. So what we actually see that those solute actually interacted with the stationary phase, and because of the difference in interaction, they have traveled at different speeds. That is, they have different rate of migration, different migration rates, different migration rates. And because of the difference of migration rate, they have eluted at a different times. As you can see here, that here, this, if you draw a perpendicular, then this is the time taken by B, you can say TB, while this is the time taken by TA. We are going to see this in terms of the retention times in our coming slides. So what happens is that your solute actually gets partitioned between the stationary phase and the mobile phase. And because of the partition, because of the different migration rates, they elute at different times. And that is why this chromatography in simple terms is called as elution chromatography. So what we have done, we have achieved separation on the basis of the partitioning, and we get a fingerprint that is called as the chromogram. So this is how the elution chromatography works. Okay, now moving forward to it, that how we are going to build up the setup. So initially what are needed is, initially we need a stationary phase, that is a stable phase. A stable phase. Generally we'll use silica, we use alumina, sometimes we use some resins like Dovex, etc., etc. So these stationary phases are chosen on the basis of the type of compound which is to be separated into its constituents. Similarly, we have to choose mobile phase. Now, mobile phase is very important in the sense that again we have to choose the mobile phase with respect to the compound which is to be separated. For example, we have to start from non-polar. So we have to start from, initially we have to start from hexane. Then we have to move towards, after hexane, we move to benzene. Okay. Then we move to polars like acetone. Then we move to more polar like methanol. And finally, we end up on water, which has the highest polarity among the common solvents. So we have to develop a polar, non-polar versus polar gradient in the mobile phase. So the stationary phase and mobile phase are chosen with regard to their interaction with the solid molecules. Now the important part is the detection. Detector, we have to use detector because it is the detector which records the signal with regard to the separation of peaks. Okay, so detector is the instrument which records the elution pattern, and moreover it is, as I've told you earlier, that it is the, it is versatile technique which not only tells you about the nature, it also tells you about the nature of constituents as well as and their quantity. That is very important, and this quantity can be calculated from the chromatogram by calculating the area under the peak. If you remember in our previous slide, we have a B eluted and then A eluted, and this elution pattern actually tells us about that how much strong interaction the different components have with the stationary phase. So we are going to explore this when we took some real life example, for example the high pressure liquid chromatography system. So we will see these real examples in our coming slides. So this is how we have to carry out our setup. That is, first of all, we have to choose our stationary phase, then we have to ascertain our mobile phase, and these two are chosen keeping in mind that which type of uh, the mixture we are going to separate. Then we have to choose the detector accordingly. That is, we can have a number of detectors, for example UV visible detector, fluorescence detector, we can have conductivity detector, we can have thermal detector, we can have a myriads of detectors depending upon the type of elution. So now comes the migration rate. Now this migration rate is very important in the sense that the effectiveness of any column with regard to the separation actually partially depends upon the migration rates of the different constituents, and this migration rate is actually measured in terms of their equilibrium constant. Let us suppose that we have a solute. Let us suppose we have a solute A. Let us suppose. Then this solute A is being transferred when we apply the solute to any chromatographic column. Then what happens that this solute actually gets transferred between the mobile phase and stationary phase. That is, an equilibrium is achieved in the stationary phase as well as the mobile phase. Now the equilibrium constant for the distribution of this analyte in the stationary phase, it may be defined as the Kd. So this Kd actually may be defined as like this. That is, activity of solute A in the stationary phase upon activity of solute A in the mobile phase. So this is how actually we define the equilibrium constant, and this Kd is actually the dissociation constant, which we are going to discuss in our next coming slide. So at this point of time, this migration of solute A is being done in stationary versus the mobile phase. Now let us suppose a case that, for example, let us suppose that concentration of A is or small or and A is some non-ionic species. Non-ionic species. Let us suppose an interesting case that A is non-ionic actually. Then in that case, what we can do, we can define this activity in terms of its molar concentration. Then Kd can be defined as Cs upon Cm. Okay. Now let us discuss the migration rate. The effectiveness of any chromatographic column actually depends upon the migration of different solutes present in a given mixture. And this migration rate can be determined in terms of the equilibrium constant. Let us suppose a solute A, for example. Let us suppose a solute A. Now this solute A, when added in the column, it gets transferred between the mobile phase and stationary phase. Now what happens is that we can write in terms of its equilibrium constant, that is A in the mobile phase equilibrated with the A in the stationary phase. Now in terms of equilibrium constant, how can we define it? We can define this transfer of an analyte between the two phases as like this: K of activity of analyte A in the stationary phase upon activity of analyte A in the mobile phase. Since this analyte A gets distributed between the stationary phase and the mobile phase, so we can fairly write like this: Kd. Now since it's a distribution, so we call it distribution constant. We call it distribution constant. And this Kd is actually very unique for each chromatographic separation. This is something you can say a characteristic for any chromatographic separation, that is Kd. And how the value of Kd actually affect the migration rates, the column performance, these are very interesting, and we are going to dwell in these aspects in our coming slides. So at this point of time, we have defined Kd in terms of the activity of analyte A in the stationary phase as well as in the mobile phase. Now let us suppose that if your analyte is non-ionic, for example, let us suppose it is non-ionic and has low concentration. Suppose, then what we can do, we can replace this activity by the molar concentration. That is, we can write like this, that is molar concentration like this. We can write Kd is equal to Cs upon Cn. That is the molar concentration of analyte A in the stationary phase upon molar concentration of analyte A in the mobile phase. Now it's a molar concentration. We can surely convert it in terms of the number of moles. So how we can define it? Number of moles of solute, okay, in the stationary phase, that S subscript is there, upon the volume of the stationary phase. Similarly, we can write N M upon Vm. And this is actually, this Kd can now be defined as the partition coefficient. This can be defined as in terms of partition coefficient. So Kd can also be called as the partition coefficient. Now, for example, suppose that in certain cases that CS gets proportional to Cn, then we can have Kd value equal to unity. This implies that the concentration remains constant for a very long range. So the two solutes actually gets migrated on the basis of their interaction with the stationary phase. So this migration actually depends upon two factors. Number one is the strength of the interaction with the mobile phase, and number two is the flow rate of mobile phase. Now this is the point which we have to discuss, the flow rate of mobile phase. Now actually there are two flow rates, and specifically we have to say in terms of average flow rate. Average flow rate. In chromatography systems, we always talk about the average parameters. Okay, so now suppose you have a column, and this flow rate may be defined as V may be defined as L upon TR. Now this L is actually the packing height of the column. It is not the length of the column, it is the packing height. This is L. This is not L. That is, L is the packing height of the column. And this TR is called as the retention time. Now, what is the retention time? At this point of time, we can say that retention time is the time taken by the solute to elute from its injection point to the final point. And this point we know it is connected to the detector. So this is the TR. Now we are going to discuss this TR in our coming slides. There is another point which is called as the flow rate of, this is actually the flow rate of the solute. Now there's another flow rate which is called defined by U, and this is defined by L upon Tm. This Tm is actually the dead time. It is called as the dead time, and sometimes you can find it written like void time. This is actually defined as the time where the interaction with the stationary phase is minimum or nil. That is only passing of the mobile phase alone. So what we actually are going to do, we are going to quantify the migration rate. So TR is the retention time. Here it was the retention time. It was the retention time. Okay, and this was the dead time. Tm was the dead time. So the two solutes actually are distinguished on the basis of their migration rates, on the basis of their TR, and the equation is V is equal to L upon TR. For example, if you are going to define the average flow rate of the mobile phase alone, it becomes U and it becomes L upon Tm, while for the solute it becomes V upon TR. Okay, so we have to keep in mind the difference between the average velocity of the mobile phase and the average velocity of the mobile phase carrying the solute with it. Okay, we have to have very clear cut distinction between the two, where L is the length of column, that is length of the column packed. Okay, it is not the length of the full column, mind that. L is the packed length of the column up to which the stationary phase is packed. Okay, now we have also given an example that methane, for example, if we pass methane, then it does not have any interaction with the stationary phase, and that is why it has zero retention and it moves or elutes very fast. While if we have some aromatic hydrocarbon which is polar in nature, it is going to retain. And the retain means that is it is going to have some interaction, and that interaction gives you TR. Okay, so any sort of interaction will give you TR, and any sort of non-interaction or zero interaction gives you TM. So migration rate actually reveals the balance of interaction forces between the components which are to separated along in and with the stationary phase. Okay, so migration rate actually gives you the idea about the interaction of different components with the stationary phase. So here comes the distribution constant. This is something very unique, something you can say this is the unique feature of every chromatographic system. That is KD, the dissociation or the distribution constant is called defined as CS, that is the molar concentration of an halide in the stationary phase upon the concentration of an halide in the mobile phase. And we have also resolved in terms of number of moles of solute upon volume of solute into number of moles of mobile phase upon volume of mobile phase. So we have also discussed it in the previous slide. Now, what are the importance of this? Why we are so concerned about KD? Actually, KD is very diagnostic. A large value of KD means this is quantity is large. This quantity is large means that we have a very strong interaction, that is with the mobile phase. That is, solute prefer the stationary phase. Solute are going to spend more time, and if they are going to spend more time, they have slower migration. Similarly, on the basis of similar KD values, we can infer the opposite. That is, smaller KD value means this quantity is high, CM is high, and CM is high, that is, your solute is preferring the mobile phase. So if it is preferring the mobile phase, it's going to elute very fast, because it is happy with the mobile phase. Okay, I'm with the mobile phase, so I'm going out. This is like this. So it is actually getting faster migration. That is, if we have KD value high for two components, we have A and B, and for B, if the KD value is high, then we get in the chromogram first peak of B, then we got peak of A. B and A. That is, here your actually B component is loving the mobile phase, and because of its love, it is eluting very fast. And if it is eluting very fast, it means that it has less retention time. So this is how KD is diagnostic with regard to the elution of different components. Now, moving forward, so polar solute in silica has high KD values. Now the polar solute actually binds effectively with the stationary phase, with the silica column, and because of this strong binding with the stationary phase, the CS is high, and since CS high, the KD value is high. This is like this, simple. The opposite is also true, that the non-polar solute in the reverse phase HPLC gives low KD value. The analogy is the same. And a very beautiful example is the sugars. Sugars are polar, and in reverse phase HPLC, they gives low KD values because they elute very rapidly. They go out of the column very rapidly. They loves the polar solvent, because the basic theme is like dissolves like. That is called as the thumb rule. That is called as the thumb rule of chemistry. That is thumb rule. So non-polar prefers non-polar, and polar prefers polar. So the moment you change the combination, the things will change. So this is about the KD value. Now, KD is very beautiful, very interesting. But the irony with KD is that it cannot be measured. This is the actually problem. The problem is that we cannot measure KD directly from a chromogram. So we have to have certain factor on which KD depends actually. Because we cannot measure KD, so we have to find some factor which actually depends on KD, and that factor can relate to KD, and that is measurable in nature? So we have the answer. And before the answer, let us, briefly uh, explore what are the factors which affect KD. Number one, we have, as already discussed, it is the polarity of the stationary phase, the chemistry of the stationary phase, the what are the different functional groups that are present, and that actually decides the retention time, that decides the interaction. Similarly, we have solvent polarities there. We have solvent polarity, which type of solvent we are using, whether we are using the non-polar solvent like hexane or benzene, these are non-polar, or we are using less polar like chloroform or dichloromethane, or more polar like alcohol, or a very polar like water, which type of solvent we are using. And this solvent polarity is important with regard to the nature of the component which are to be separated. Similarly, temperature also comes into play, and we will discuss the effect of temperature on a very large scale in GC when we discuss the gas chromatography, where temperature controlling is one of the very vital things for the effective separation of different components of an analyte. Similarly, pH also becomes very important in case of ionizable compounds. For example, if we have some acid or bases, then pH also becomes very important. Similarly, the presence of modifiers, that is the ion pair reagent, these directly affect the value of KD. Now, what are the actually advantages of KD? The advantage of KD is that it's a direct measure of the partitioning. On the basis of the KD value, on the basis of its magnitude, we decide that it is partitioned where, that is, it is more towards the stationary phase or more towards the mobile phase. So this is the advantage, that it give you a direct link, a direct measure of the partitioning between the mobile phase and the stationary phase. It gives you a direct measure, but at the same time it has a very strong limitation. So what are the limitations? There are certain limitations of KD also. Besides all these advantages, there are certain limitations also. The first limitation is, of course, it's KD. KD cannot be directly measured. This is the foremost, directly measured from the chromatogram. From the chromatogram. That was the first limitation. And the second limitation, that it is strongly matrix dependent, because the polarity and non-polarity comes into play. So if we have combination of polar, then it's fine. And sometimes it interacts very much with the solute, and the elution becomes a problem. That is why its matrix actually sometimes creates problem. And we cannot predict a sample before running, because we never know what type of interaction it is going to hold. So this is the limitation. Okay. So now, with regard to the distribution constant, what is the role of KD actually? KD actually gives an idea about the retention. Now, this KD actually is directly linked with the migration rate we have seen in the previous slide. And at the same time, this KD value influences the peak width and separation efficiency. Now, this point is worth discussing, that influences the peak width and the separation efficiency. Now, if you remember, we have drawn a chromatogram where we have plotted detector response, okay, on the y-axis, and we have plotted time. So for a two-component system, we have seen that initially we get a small peak, then we get the peak of component 1, and then we get a peak of component 2. So this time is running, and these are the detected responses. For example, let us suppose, let us call this B, and this is called as component A. Now, for an ideal elution, these two peaks must be as far as possible. That is, they must be as far as possible within a given time. It's not that they are taking 2 hours or 3 hours. If they are taking more time, then again it will compromise the efficiency of the column. So they have a clear cut separation, and the speed peak width, that is to be kept minimum. That is, the peak must be Gaussian type. It is not like this. This is a bad chromatographic peak. This is not ideal. The ideal is the Gaussian. It is called as Gaussian peak. We will discuss this Gaussian peak. And this Gaussian have a lower fronting. This is called as the fronting part of the peak. Fronting. And this is called the trailing. The trailing is not too much. This is called tailing. And this is actually the central part. That is the part where most of the migration take place. So this KD value actually influences the peak width, that is the peak width, and it also influences the separation efficiency, because a good separation means that is the peaks must be as far from each other as possible within a given time. That is, you have to take time also into account. So solute with close K values, for example, if you get a separation like this, then the values are too close. And here you can say that the distance between the peaks is not well defined. Or you can say peaks are not separated. Similarly, if you add some performance factor and you get this type of peak, although the peaks are separated, but they are wide. So then ideal chromatogram should like this. You can see this is an ideal chromatogram where you have good separation and the peak width is also to be minimized. So what we infer is that KD value actually dictates the distance, and they also dictates the width of the peak. So width of the peak must be kept as small as possible, and the separation of the two peaks must be kept as big as possible, keeping in mind the time. Time is also important with regard to deciding the efficiency of any chromatographic column. So solutes with K, close value of K does not give gives poor separation, and we have optimal elution when K values are significantly different. So K values can only be different in cases where we have the clear cut separation like this. Here the K value of, for example, of B and K value of A are different in terms of their distribution constant. So this is how the role of KD. So with this, thank you very much.